So far we have seen these kind of graphs representing vapor pressure versus temperature. It's about time now that we try to quantify these trends that hopefully we have understood in the past. To that end, we have what it's known as the Clausius-Clapeyron equation, and you have it here. And before you just jump into plugging numbers into it, I want to make sure that you understand what this equation is telling you. And hopefully it should make some sense. First of all, this relates the vapor pressure with temperature and the heat of vaporization, or the enthalpy of vaporization. It should make sense that the higher the temperature, the higher the vapor pressure will be. Okay? And also the higher, or another one if you will, the higher the enthalpy of vaporization, because it's in the denominator, it means that the pressure is lower. Okay, so that should make some sense. We already have said that, and you should be able to have a mechanistic and an atomic explanation for that. All right, so do not get carried away by the math, because it's more important to understand it. Notice that if we have a logarithm, so if we raise this to the exponential, you have what you see in these graphs. You have an exponential dependence on temperature for the pressure. So that's what these graphs show. It's an exponential, and now we know the expression. The vapor pressure is equal to E RT delta. That's a so-called Clausius-Clapeyron equation. But most importantly, you should be able to understand it from the atomic perspective and in terms of intermolecular forces. All right. It's also useful to use Clausius-Clapeyron equation at two temperatures. And to do that, we need to understand what's happening at two different temperatures. Well, we already said that as the temperature increases, the vapor pressure increases. And please do not try to apply the PV equals nRT here. This is equilibrium between liquid and gas. In PV equals nRT, you had a pure gas, and this would not be the vapor pressure. This is the total pressure of the gas. So please do not apply blindly PV equals nRT. What this graph is trying to tell you is that the fraction of molecules ready to be vaporized will always be larger the larger the temperature is. Okay, so Clausius-Clapeyron equation can be applied at different temperatures and relates to different vapor pressures. So you can combine two Clausius-Clapeyron equations. So again, if you do logarithm of P delta A, RT delta H, and you combine for a given 1 and 1, you combine this, it's easy to see that if you have then at two different temperatures, you have two different vapor pressures, being the enthalpy of vaporization the same. You combine these two and you obtain this typical form of Clausius-Clapeyron equation. How can we use this? Well, let's solve a problem and maybe we can figure that out. So in this case, it's asking you to calculate the vapor pressure of methanol at a certain temperature, knowing that ethanol boils at this temperature. Alright, if it boils at this temperature, it means that when the vapor pressure is 1 atmosphere, that's what boiling is, right? When the vapor pressure is equal to the atmospheric pressure, so let's call this P1, T1 is 337.8 Kelvin. So what it's asking is, what is pressure 2 such that temperature 2 is 12 Celsius, and I'm going to convert it into Kelvin. Okay. So notice that it's giving you already the enthalpy of vaporization. So what it's asking is we need to find P2. So logarithm of P2 divided by 1. How much is P1? 1 atmosphere. Okay. And enthalpy of vaporization, it is 35.2 kilojoules. So I'm going to convert it into joules. Careful. joules per mole divided by R. R is the gas constant, and 831 joules over mole and Kelvin. How much is T2? Is 1 over 12 plus 273, and T1 is, oops, this is negative. It's 337.8. You have one single unknown, so P2, if I call this whatever x, P2, sorry, I forgot the negative, is the exponential of this negative x, this value, this number. Okay, so there you go. We found the vapor pressure at this given temperature. This is a typical application of Clausius-Clapeyron equation.